This is 2.1 and 2.2, conditional statements and definitions, and we'll start by defining what a conditional statement is. It's got two parts, a hypothesis and a conclusion. And conditional statements can be written in if-then form, if this, then that. When they're written in that form, the if part contains the hypothesis and the then part contains the conclusion. And we can also represent conditional statements symbolically, and when we do that, the hypothesis is often represented by the letter P, and the conclusion is often represented by the letter Q. So in general, when we're talking about conditional statements, we may say if P, then Q. And so the hypothesis is with the if, and the conclusion is with the then. You may also see it written as P, and then an arrow, and then Q, and that would be read as P implies Q. It's just another shorthand way of saying if P, then Q. Conditional statements can also be represented by a Venn diagram. So in general, in Venn diagrams, whatever is in this innermost bubble right here is also in this outer bubble. So the hypothesis could be represented by the red region, and the conclusion would be represented by the blue region. Anything that's in the red region is also in the blue region. If P, then Q. Next, pause the video and see if you can identify the hypothesis and the conclusion in the following statement, and then also represent it with a Venn diagram. The hypothesis is you vote in New Hampshire. And notice how the word if is not included as part of the hypothesis. It's just the phrase you vote in New Hampshire. The conclusion is you are an American. Again, notice the word then is not included as part of that conclusion. If we were to represent this with a Venn diagram, remember the conclusion would be the outer bubble, the hypothesis would be the inner bubble. So in the inner bubble we would say you vote in New Hampshire, and then in the outer bubble would be you are an American. The converse of a conditional statement is formed by swapping the hypothesis and the conclusion. Go ahead and pause the video and try writing the converse of the statement in example number 1. And what you hopefully wrote was, if you are an American, then you vote in New Hampshire. Again, we're forming the converse by swapping the hypothesis and the conclusion. Now, you might have noticed that this statement isn't necessarily true. You can be an American but vote in any one of the other states as well. So when you have a statement and form its converse, it's very possible that either both of the statements could be true, both of them could be false, or one could be true and the other could be false. So when you take a statement and write its converse, the meaning of the statement is not necessarily going to be the same. One of the things that we'll be working on this year in geometry is proofs, and proving that certain statements are true. And in order to do that, we need to show that it's true in all cases. Which can be kind of challenging, but we've got some methods that we'll use in order to do that. Proving that a statement is false is much easier because you only need to show one counterexample. And a counterexample is just an example that demonstrates that a statement is false. So in order for a statement to be true, it has to be true in every single case. If there's one case where a statement is not true, then we say the statement is false. In example 3, we need to show that the statement is false by finding a counterexample. And the statement reads, for all real numbers x, the expression x squared is greater than or equal to x. Now there's plenty of cases for which this statement is true, but it's not true for all cases. And so our goal here is to find one of those examples, one of those values of x that shows that the statement is false. And in order to do that, it's helpful to try some different types of numbers, positives, negatives, fractions, decimals, and also to organize our information in a chart. So I'm going to start by creating a chart. Since the numbers that we're comparing are going to be x and x squared, I'll create a column for both of those, and then one final column so that I can summarize my findings in each of those cases. Is x squared greater than or equal to x? Pause the video and try some different values for x to see if you can find a single counterexample. So I'm going to try some different values for x. Let's say that x is 2. X squared would be 4. Is 4 greater than or equal to 2? And that's a true statement, so that's not a counterexample. What if we try the number 1? X squared would also be 1. Is 1 greater than or equal to 1? That's still true. What if we try 0? X squared is also 0. Is 0 greater than or equal to 0? Again, a true statement. If we try a fraction, though, what if x was 1/2? Squaring 1/2 means 1/2 times 1/2. That's 1/4. Is 1/4 greater than or equal to 1/2? That's false. So this right here would be our counterexample. The counterexample is x equals 1/2. And I'm sure there's others. Perhaps you found a different one, but there's no need to continue because we found one case that shows that that statement is indeed false. Many mathematical rules and theories come about because somebody notices a pattern, and then the pattern is either proven true in all cases, or somebody comes up with a counterexample. But it's also possible that a statement can be proven neither true nor false. And here's an example of that. It's called Goldbach's conjecture. And if we take a look at the numbers that are down here in these various examples, take a look at these numbers right here. Those are even numbers. Goldbach noticed that many even numbers greater than 2 can be written as the sum of 2. What? Let's take a look at these other numbers. Remember, sum means addition. So all of those even numbers are written as the sum of 2. Now it looks like it might be odd numbers. Many of them are odd, but there's also these 2's here that I circled. So instead of odd numbers, it's prime numbers. Take a moment and pause the video. See if you can come up with some examples for 16, 18, and 20. And there's a few examples. 16 can be written as 13 plus 3, 18 can be written as 11 plus 7, and 20 can be written as 13 plus 7. And you might have had a different example for each of those, and that's okay. There were several of them that worked. And next we have a definition. Two lines are called perpendicular lines if they intersect to form a right angle. And here's the notation. Notice the upside down T stands for perpendicular. The definition of perpendicular lines is a conditional statement, so it can be written in if-then form. So pause the video and see if you can write the definition in if-then form, and then also write its converse, and then we'll decide if the converse is true or not. So in if-then form, it would be if two lines are perpendicular, then they intersect to form a right angle. The converse of that statement would be if two lines intersect to form a right angle, then they are perpendicular lines. that converse is also true. And the case with all definitions, when you write it in if-then form and then also create the converse will also always be true. That is something that's always true of definitions. And here's another definition. A line perpendicular to a plane is a line that intersects the plane in a point and is perpendicular to every line in the plane that intersects it. So right here in the diagram, so let's say that's the point where the line intersects the plane. If I were to make all of the lines in the plane that also go through that point, in order for line N to be perpendicular to plane P, line N has to form a right angle or be perpendicular to every single one of those red lines that I'm able to draw through that point where line N crosses the plane. And here's several point, line, and plane postulates. Remember, a postulate is a statement that is accepted without proof. We saw some of these in Unit 1. Using your knowledge from Unit 1, see if you can fill in all the blanks for these 7 different postulates. Through any 2 points, there exists exactly one line. A line contains at least 2 points. Now, a line actually contains infinitely many points, but in order to create the line, you need to have 2 points to start with. Postulate 7 is if 2 lines intersect, then their intersection is exactly 1 point. Postulate 8, through any 3 non-collinear points, there exists exactly 1 plane. And we say that those 3 points determine the plane because there would be exactly 1 plane that would contain those 3 points. And it's important for them to be non-collinear points because if they were collinear or all on the same line, then there would be more than 1 plane that would contain those points. Postulate 9, a plane contains at least 3 non-collinear points. So this is very similar to postulate 8. Postulate 10, if 2 points lie in a plane, then the line containing them lies in the plane. And postulate 11, if 2 planes intersect, then their intersection is a line.